This afternoon I'm going to talk to you a little bit about material science for structural engineers, and this is mainly concentrating on how we derive fatigue curves and how we validate the materials data to put in the database so you can use that for analysis in design life and Cliff works. So two main sections. Firstly, looking at producing good materials data, your source material, specimen design, design the experiment, and then what analysis you have to do in order to generate the data that you can then use for your calculations. And then a little bit about a couple of things we added into ENCODE 10 in terms of materials, in terms of the new database, standard database, and some little couple of additions to Materials Manager. And maybe a software demonstration depending on how the timing goes. Okay, so producing good materials data. So why do we need this to start with? I think I'm contractually obliged to put a 5-box trick up from a long while ago, so that's one. So we have three major inputs to any fatigue analysis: the geometry, the loads, and the materials, and they're all as important as each other, and you need accurate data on all three of those. So you need good materials data in order that whatever prediction you're going to make is going to be as accurate as it can be. And what drives the performance of the material? Well, in terms of the metallic materials, the basic material, whether steel, aluminium, the basic composition of that, so the alloying elements that go into that. So that gives you the sort of basic performance of what the material is. But even with materials which are directly equivalent in terms of their composition, you've still got the manufacturing effects and other things that can quite markedly affect the performance. So whether it's cast, forged, sheet, rolled, things that affect the microstructure that then affect what the fatigue performance is. So that all affect the microstructure, have quite a large effect on the fatigue performance. In terms of the material itself, how clean that is and how good the composition is and how variable is a factor in whether you should look at different sources of that material. And then one quite often forgotten is the surface finish or surface treatment. So if you have added any surface effects to this, can also quite largely affect the performance. And you can look at those in two different ways. So you can either do them in terms of the materials tests or within the software take account of those effects as well. So generally speaking, in order to generate the best parameters for your optimum design purposes, you probably need test coupons from the component you've designed. Is that the ideal situation? Now, if you haven't got a component, or you've designed a new component, that's pretty difficult. And quite often difficult even if you have got a design, it's too far down the process. So you probably want to do that sort of an ideal situation where you might have a component, you want to pull the specimens out the areas you're interested in, if you've got enough material there, and you get specimens out there. It's quite often not something you can't do. So you've got to step back from that sometimes and then generate the samples to give you the same material, composition, surface finish, and microstructures you would get in the final component. So you've got to be a bit careful about how you generate the material itself that you use in the test specimens. Once you've got that, there's a set of standards we adhere to in terms of what material samples to make. This is some example of the cylindrical ones we use. So cylindrical for a lot of the things. If it's sheet steel, you can do sheet, similar sort of proposed design, where you've got a central section, gauge area where you've got the specimen, the actual failure point you want, with a fairly smooth stress profile in that area to get a sensible failure, and then range in size from quite small to quite large, and pretty much want to aim for the largest sample you can for that for the material you've got available, if possible. Also with sheet specimens, you've got to be a bit careful with the edges, break the edges, clear those off. And in terms of surface finish, generally for most materials you do this in polished form, so not mirror polish, but all the machining marks removed. So for a baseline material sample, polished specimen, that gives you the best fatigue performance, no effective surface things. You then might want to do samples at your surface finish. So you can either take account of that in the software or you can do that in the materials data. So if you want to be really accurate and you generate the same surface finish on your components all the time, you can use the samples with that surface finish to get you more accurate data. Excuse me. It's an example of a slightly out of scale test rig. So this is an example of the setup for one of our rigs we've got on the lab. I think we've got 10 10 rigs in the lab, ranging from 10 kilonewtons to 250 kilonewtons, depending on sample size and what they use for, and also high and low temperature capability. So there you see the actual test rig section, and there you have the sample, and in this case with the extentometer attached, so you're measuring the strain, load cell at the top, measuring the stress or the load applied, and then the actuator at the bottom. Definitely out of scale on that part. And that's one of the examples of one of the rigs actually in the lab. So there you've got just about visible test specimen, the smallest bit on the left, with the extentometer attached, and then a pseudo old analog test interface, now in digital form, but I guess it makes the test engineers feel okay. There's rigs what we used to use before in terms of analog, we've now got a digital version of it. So all the control on that screen, and then all the feedback and analysis on the second screen. So there you've got hysteresis loops coming out directly, feedback data, checking the test as it's going through. And then what sort of testing do you have to do in order to determine the fatigue performance? So two major types. I guess the first that was in 18th century, 19th, Bowler, 1850 something, yeah. So original Vola did this sort of test where you'd got axles where you're failing. You wanted to do simulate what happened in the lab, simulate what happened on the trains. So brought the axle in, hang a weight on that, rotate it. You run it to constant stress level, and you get failures due to that. And that's pretty much what that stress life curve is plotting, where you've got stress level, cycles to failure. And in terms of SN, stress life, generally run a series of samples at a particular level to get a distribution of your failures at that level, several levels, and then you can plot a curve through that in terms of your SN performance. Generally, for a lot of SN data in the published domain, you've got an R ratio of 0.1. We'll come back to that in a minute in terms of what we use. So that's the one method. Stress life, we do that, but not our general method for most of the fatigue materials we generate. Generally, we look at doing EN testing, so strain life. So where you, in this point, you're adding a constant strain amplitude, so that's why you need the extentometer on the sample, so you're actually measuring the strain in the component. Two reasons for doing this: gives you more accuracy, less variability, and also it's controlling the parameter that actually governs fatigue. So you're actually controlling the strain, that's your controlling factor, and you get much more accurate data. And the one difference you notice from the plot, what we tend to do is populate the entire curve. So you're not running multiple points at a single level. You're trying to fill this curve in as much as possible to get the best fit over the entire area of the curve. There again, simply plotting log strain, cycles to failure. And in this case, reversals to failure. Slight difference between SN and EN. EN, all the theory was postulated in reversals, so it's all in reversals, whereas SN generally, it's all in cycles. So that gives you all the base curve. So we've got some material samples. We've fitted that curve. That gives you a 50% fit on the curve. So basically at that point, when you hit that curve, 50% of your samples have failed, 50% haven't. It's not really where you want to design to, generally. So generally we will add into the database a 97.7% certainty survival at 95% confidence interval. So you've then got a design curve which drops down to that point there. So you're much more sensible place to start your design. So that's our base version we will put into the database. We can generate whatever we need to in terms of what the customer wants, but that's generally what we put in by default. And that, in combination with the variation in loads and geometry, gives you satisfactory performance equivalent to about 6 sigma. So if we look at, that's a typical data set. So if we're looking at, initially I'm looking at the number of samples, and how some things can affect the quality of the data you get. So this is one of our samples from the new premium database, where we've got, in this case, 25 results, and that's just about the minimum we use for, well, it is the minimum we use for all the data sets we put into that database. Occasionally we might do less for particular customer requirements, but generally that's what we consider to be the minimum to use. So that's basically showing you the data without the plots. And if we actually look at their analysis software we've got that generates the data, I'm going to put the curve first, yes. So this just gives you looking at the variation between number of samples tested. So we've got the base curve, get the colours right. Green is the base curve, purple is the design curve, and you see the other two lines there crossing over are if you've just cut the number of samples down, so between either 10 or 15, just looking at the effect of what just reducing that number of samples can have. So you're still covering the complete area of the curve, you've just got a bit less accuracy in terms of the variation. You know, look at that in terms of the data points, so that's the same data plotted from 10 tests, so we're still covering the complete area. You'll see there's quite a large difference between the design curve now and the base 50% curve because we've got much less samples. You go to 15, you're bringing them much closer. We're also changing the actual base curve data itself slightly. And then for 25, much closer. So you've closed down this variation because you've got a lot more samples included in that data set. If we look at the distribution of these results, so you've not only got to generate enough points, you've got to get them in the right area. So you've got to cover a significant number in both the elastic region and the plastic region to get the fit correct in both areas. Now in this case, we've got the design curve again, and now we're looking at not enough points in the elastic area on the red point, and you're actually crossing the design curve. It's going that far. It's quite a long way out in terms of life. So practically speaking, that's not that difficult, but also at this end, you're going non-conservative. So it can be a bit of a problem, and that could be either way around, depending on where the data is not fitting. So in this plot, we're now looking at the same thing, 10 specimens, but now too few in the plastic region. And at this point, we're actually moving the curve as well quite a bit. So we're also making the design curve less accurate and losing accuracy in the top end as well. And too few in the elastic, quite a bit of variation now in the elastic region. So not enough points down there. And change the curve position again. So in terms of what we do in terms of data we generate in the database, testing strain control gives us the best results, most consistent results, and the end data is what we tend to use for most of the analysis when that's generally the most of the analysis you pick. So that provides the required information for design life and glyph works for doing your fatigue analysis. We also get a stress life line at r equals -1 from that data, so you can generate the stress life line as well, so you get that for free. Thing to remember again, that's at R ratio -1 because that's what we've done the strain life test, and that may be not what's in the literature for the same material. Generally, most of that would be at 0.1, not at -1. And we deliver both regression parameters at the 50% curve and also design parameters at 97.7 and 95% confidence intervals for all the materials. And we try and test sufficient specimens, so a minimum of 25, occasionally up to at least 40 sometimes, so up to that sort of number, definitely a minimum of 25 now in terms of what we think is necessary. Okay, so that's sort of our basic procedure for generating good materials data. I just want to cover a couple of things that we've added in to version 10 to do with materials. So first of all, the materials manager. We've added some extra fields to all the base data sets. So there's about 11 new fields in terms of specification information. There's a new filter option, and we've also added the ability to license protect the database. So in terms of the new specification fields, there's 11 new fields, and these are to cover equivalent specifications for each material. So we've got the base spec that is generally in the name of the material that sits in the database, and there are 11 other fields. So if there is an equivalent, we will put that in. So this is equivalent as close you can see in equivalent, same composition, nominally the same material. You can still get differences, but it's a nominal equivalent. And then we've also had the ability to filter the materials based on any other parameters in the database. So you can search through for an equivalent specification for a particular standard, search through a particular UTS range you're after, particular yield stress, or whatever any other parameters are. So a little bit easier to find the materials in the database. In terms of the standard database that's available, that, as of 9.1, had almost 200 materials in it, almost 200 materials data sets, mixture of SN, EN, various different ones. We've added another 200 plus materials to that. So that is a combination of 43 sets from the AISO, American Iron and Steel Institute material data set, where they published a set of material data, actually the actual fatigue results, and we've analysed those back with our own procedures and put the EN data in for that. And then also a series of data sets from the FKM handbook. So AISO bar data, we've done the analysis, complete set of curves in terms of EN, SN and stress. Yeah, stress life's in as well, yeah. So a full set of curves, 43 data sets, and generally with all the equivalents in terms of what the materials are. And the FKM, quite a lot of data sets. This is synthetic data generated in the FKM standard, so it's not real measured materials data, synthetic data for particular data ranges and different material types. And that's Dangvan and Stress Life. Now also what we've introduced at version 10 is a premium database. So this is an unprecedented collection of real fatigue data we've measured in our own lab. So a large number of materials, data sets that we've measured the data and done the analysis, so we know the pedigree of the data all the way through from the material all the way through to the results. Currently includes many commonly used steels and aluminiums. As I say, all measured in our own material. I keep forgetting what we call the lab. Advanced Materials Characterization and Test Facility, or our lab. They're very high quality fatigue parameters, including statistical estimates of the scatter and certainty of survival. And we intend adding materials to this as we go through. So what's in at the moment? It's license protected and only available through the CDS licensing system. It's currently got 72 materials in, mostly steel, some aluminiums, a bit of cast iron, and EN design curve, and an SN stress life curve for all of those. And a pretty full set of equivalents where they are available. That's the current list. I think there's a data sheet outside as well that we've prepared. So that's the list of material specs we've got in so far. As you see, mostly steels currently, a few aluminiums. So that's what's in at the moment. We intend releasing probably 3 times a year in terms of updates to this. So our lab is pretty much concentrating on generating data for this database, along with some customer work, but mainly concentrating on this. And we're probably going to be releasing 8 to 10 3 times a year in terms of materials. And those are the next 2 lots that are coming out probably in June, first lot. So some extra steels, some magnesiums, titaniums. At the moment we're filling the gaps in on terms of data we think we should put in. We've also had some requests from customers, so if any materials you do want tested you think would be generally applicable, I think we're tending to put generally applicable materials in, so if there's something a lot of people are interested in, we will try and put it in. And then a second lot, probably September, October maybe, in terms of some more mags and titaniums. So most of the testing on this lot is already complete, we're just finishing the analysis off before the release, and testing on these is about 50% through. So this is room temperature, EN, SN data currently. We're currently looking at what we should do in terms of other materials, so non-metallics, TMF, high temperature materials. Well, the testing's a bit more expensive, but it's more worthwhile in terms of what we give the customer in terms of a good data set. Yes. Okay, just a quick look at the software, if I can get out of there. So that's the new premium database. So you've got the 72 materials. As I said, each data set now has got a full set of equivalent material specifications. And the new change in terms of the searching, you've now got a filter option. So you can pick on base material type, any specification from an EN spec, UTS minimum 500. And then any of the properties for the individual data set you can pick, so you can drill right down to any of the individual fatigue properties. and do a search, and you've got a list of the ones that meet that requirement. So you can drill down and find any material set much more easily. Let's have a quick look at the standard one. That's now the standard database, and now got 400 plus materials. So I mean, before it was quite filled up with published data, some generated data. Now it's pretty much some more useful data sets in that freely available database. Okay, any questions?